Okay, in this video we are going to be doing a limits review for AP Calculus. The idea here is that you have finished the course and you are now at the point where you're actually reviewing for the exam. It's possible this title card is kind of overselling how graphically amazing this video will be, but if you go through these problems, I think you'll get a pretty good review. So with all that said, let's get started. All right, number one here is to evaluate the limit as x approaches 3 of x cubed minus 27 over x minus 3. I mean, step one on any limit is just to try to plug in, but you can see that you'll get 0 on the top and you'll get 0 on the bottom. So we need a different approach. The first approach that I'm going to try is to factor. So let's say option 1 is to factor. So limit as x approaches 3. And I need to factor a difference of cubes. So it's going to be x minus 3 and then x squared plus 3x plus 9. So when I have to factor a difference of cubes, I use this, which is the only way that I can personally remember it. So it's the same sign. This is the opposite sign. This is, well, both of those are always plus. So it goes, we got the same sign, then we have the opposite sign, and then we have always a plus. And that's how I always remember that. All right, divided by x minus 3. We can cancel, so this will be the limit as x approaches 3 of just x squared plus 3x plus 9, which if we plug in is 9 plus 9 plus 9 is 27. Okay, so that's option 1. Option 2. I'm going to try to vary up the colors here. I'm not really good with colors, so here we go. Option 2 is, I look at this and I think this looks a lot like the definition of the derivative. So if it is, it would be the limit as x approaches a of f of x minus f of a over x minus a, which would make f of x x cubed and a would be 3, which means I'm just trying to find f prime of 3. So f prime of x is 3x squared. F prime of 3 is 3 times 3 squared, which is 27, which is the same answer, obviously. And then I'm going to do it one more time. And this time, I'm going to use what I think is probably everyone's favorite approach, which is L'Hopital's rule. 3 L'Hopital's. All right, so we already established it's 0 over 0, so I'm just going to do the limit as x approaches 3 of 3x squared, the derivative of 27 is 0, over the derivative of x is 1, the derivative of negative 3 is 0, so we just get 3 times 3 squared, which is 27. No matter how you do it, that's what you're going to get. So 3 different approaches, all of them lead to the same answer. Doesn't really matter which one you choose. I think that most people probably actually go with this one, because once you learn L'Hopital's, it's like all you ever want to do. All right, let's look at the next question. Graph of f is shown to the right. And what value of x does f have a removable discontinuity? All right, so although the question is removable discontinuity, and you can look, this is where you have your removable discontinuity. So there's a removable discontinuity at x equals 2. I'm going to write that down. So removable at x equals 2. Now, we don't have to give a reason because, I don't know, this is probably a multiple choice question or something, but my reason would be because the limit as x approaches 2 of f of x is 4, but f of 2 is, the key thing here is that it's not 4. It doesn't even need to exist, but it's definitely not 4. So that would be my reason. So if the limit exists, but does not equal the value of the function, removable discontinuity. There's a couple of other things happening here. At -1, so at x equals -1, there's a jump discontinuity. And if we had to justify a jump discontinuity, it'd be that the limit as x approaches -1 from the left is 3, and the limit as x approaches -1 from the right is not 3. I'm going to say it's 2.5 and just like guess. Which you really shouldn't do if you're justifying, but I don't want to work it out, so there you go. Actually, I think that's right, because I think the slope here is over 2, up 1, so if we go back 1, we'd go down 1/2. So I do think that it's that. So we got two finite values that are not the same value. So the limit from the left exists and is finite, limit from the right exists and is finite, but they are not the same thing, therefore jump discontinuity. And there's a final type of discontinuity here. So this is going to be so it's an infinite discontinuity. I usually use disc at x equals -2, and my reason would be because the limit as x approaches -2 from the left of f of x is infinity. So when you're dealing with an infinite discontinuity, you just need the limit from the left or the right to be infinity or negative infinity, and you are done. That's going to have to be an infinite discontinuity. So the common name for this is a vertical asymptote. The common name for this is obviously a jump discontinuity. That's the common and the official name. And then the common name for removable is a hole. So the answer to the question is this, but deep dive, we did all the extra stuff. All right, question number 3. The graph of f is shown to the right and consists of 3 line segments. True. Evaluate the limit as x approaches 1, the integral from -2 to x f of t dt minus 3x over 4e to the x squared minus 1 minus 4. All right, so step 1 is try to directly evaluate this thing. And so that would mean doing the integral from -2 to 1 of f of t dt, and then minus 3 times 1. So the integral is going to give us, that'll be -1. This is +1, so -1, +1. Those cancel. And then we're just going to here, so that's not a good line. Let's do there. That's 2, that's 3. So we get 3 minus 3, which is 0, and then in the denominator we get 4e to the 1 minus 1 is 0, minus 4 is 0. Okay, so the limit of the top is 0, the limit of the bottom is 0. We can use L'Hopital's on this. To use L'Hopital's, we're going to have to do the second fundamental theorem on this part. So let's do this. So we'll say the limit as x approaches 1 of the derivative of the integral from -2 to x f of t dt is going to be f of x times 1, and then the derivative of -3x is just -3 over the derivative of 4e to the x squared minus 1 is going to be 4, and then 2x e to the x squared minus 1 because of the chain rule, and then the derivative of -4 is 0. So now if we try to plug in, we will get f of 1 minus 3 over 4 times 2e to the 0. So what is f of 1? F of 1 is 4. So we get 4 minus 1 over 4 times 2, 8. So nope, we don't get 4 minus 1, we get 4 minus 3. 4 minus 3, so we get 1 over 8. And that is the answer. If we want to clean up our work a little bit, we would go back up here and say the limit. I don't know that we can clean up our work here. That's the limit of the numerator and the limit of the denominator, but I don't know what we can really do about it. So I'm going to leave it as is. All right, looking at number 4 here. Given that f of x is limit as h approaches 0, secant squared of x plus h minus secant squared of x all over h, what is f prime of x? So the key thing here, I think, is that this is sort of a trick question. This is the limit definition of the derivative. This is already the derivative of secant squared of x, which would be 2 secant of x times the derivative of secant of x, which is secant tan. Okay, so really, f of x is 2 secant squared times tangent. Okay, and the question is, what is f prime of x? So f prime of x is going to be really messy, and maybe I didn't think about that when I wrote the problem. So I'm going to go first and then second, right? So first, changing colors apparently. Derivative of the second, derivative tangent is secant squared. Plus second, derivative of 2 secant squared is going to be 4 secant times the derivative of secant, which is secant tan. Let's see how this cleans up, if at all. So we're going to get 2 secant to the 4th plus we got 4 secant squared tan squared. Which, I mean, there's stuff you can do here. I don't think it's worth it, but it is worth noting that 1 plus tan squared is equal to secant squared. So, like, you have the option of writing this entirely in terms of tangent or entirely in terms of secant if one of those helps you out, which I don't really think it does. So I'm just going to kind of, like, end my work on that problem there. Okay, let's take a look here at number 5. We want to evaluate the limit as n approaches infinity, the sum from k equals 1 to n of the quantity 3 minus 4k over n cubed, and then times 4 over n. So as soon as you see this thing, like a limit to infinity and a summation, you kind of know this is going to be the limit of a Riemann sum. So now what we need to do is we need to figure out what the function is, and once we know what the function is, we want to figure out what we are using as our bounds, and we'll just have a definite integral. So first thing I want to do is I want to look at this thing and figure out delta x. So I think delta x is sitting right here. So I'm going to say that delta x is 4 over n. Now that I've made my choice of delta x, I look and I see if I can try to figure out what x sub I is, like the thing, or x sub k in this. I usually use I as my index. AP exam almost always uses k. So I look for the place where it looks like I'm subbing something into a function. So I kind of have two choices here, and I think that this is actually a trickier problem than maybe a lot of them. I think that what I'm going to do is just say that this is x sub k, and I have a reason for that. My reason is I think that the function that we're dealing with, I think f of x is going to be the quantity 3 minus x cubed. So I want to be really careful here because it's 3 minus 4k over n, not 3 plus 4k over n. If it was 3 plus 4k over n, then I would say that x sub k is 3 plus 4k over n and just kind of like live my life. The problem there is the way that it's written, 3 minus 4k over n, that would be like delta x is negative 4 over n, and I don't want to deal with that. So I'm thinking that f of x is 3 minus x cubed, and now I think that that means that x sub k is just 4k over n. And then once we have x sub k, we'll find x sub 0, which means plug 0 in for k. So you get 4 times 0, 0 over n, which is definitely 0. And then x sub n, we plug in n for k. So we have 4n over n, which is just 4. So we're going from 0 to 4 here. Okay, so now that I have this, I'm going to make all my substitutions and write a definite integral. So I think that, so I've identified already the function, but like at this point, usually I would be trying to identify the function. I think that the function is, I don't think this yellow color comes through very well. So I think the function is like the overall like 3 minus x cubed. I think that this is my function as previously mentioned. All right, so I'm going to write the integral from 0 to 4 of my function, which is 3 minus x cubed dx. All right, so we have multiple ways that we can do this. We can say that You just integrate it, which is actually the easiest thing to do. So 3 minus x cubed. So there should be a negative by the chain rule. So this will be negative, negative 1/4. And then 3 minus x to the 4th from 0 to 4. We could also do u substitution, which is maybe like a safer thing to do, but I'm not going to do it. Well, I mean, I'll go back and do it because why not? But if I plug in 4, I get negative 1 to the 4th. And then if I plug in 0, I get 3 to the 4th. And then that's going to be negative 1/4 of 1, and then minus 81, which is negative 1/4 of negative 80, which is 20. So I think the answer to this question is 20. Okay, so I also mentioned that we could have just done u substitution, which, you know, is a good choice and like the safe choice. Let me just move some stuff here. Let's move u, and let's move u. And so what we could have done is we could have said that u is 3 minus x, negative du is dx when x is 4, u is negative 1 when x is 0, u is 3. So we'll get negative integral 3 to negative 1 of u cubed du. But then we want to flip that and change the sign, so it'll be negative 1 to 3 of u cubed du, which is going to be 1/4 of u to the 4th from negative 1 to 3, which is just going to take us back here. So either way you do it, that's how it's going to come out. All right, so that's number 5. Okay, let's take a look at number 6 here. Let f be the function defined above. Which of the following statements about f is true? Continuous differentiable, continuous not differentiable, differentiable not continuous, that's impossible. Cannot happen. Neither continuous nor differentiable. All right, let's see. So continuous, we need to look at the limit as x approaches pi over 2 from the left of f of x, which is going to be the limit as x approaches pi over 2 from the left of, if you were to the left, you're here. So cosine of 3x, which will just be the cosine. Cosine's a continuous function, so we just plug in. And then the cosine of 3 pi over 2 is 0. You should definitely know your unit circle, in particular the quadrantals it's amazing for, but like all the unit circle would be useful. And then we need the limit as x approaches pi over 2 from the right of f of x, which will be the limit pi over 2 from the right of, if we are approaching from the right, boom. So that'll be 3/2 tangent of 2x, which is, tangent's not continuous, so we do have to like worry about this, but let's just sub in pi. Tangent of pi is 0, so this is 0. And then we also technically need f of pi over 2, but the limit from, because of the way it's defined, the limit from the right is equal to the value, so this is also 0. Okay, so definitely continuous. So d is out. Now we just need to see if this thing is differentiable. So what I'm going to do is I'm going to find the derivative of each branch and see if those match up. So f prime of x. Okay, the derivative of cosine of 3x is going to be negative 3 sine of 3x. And that'll be when x is less than pi over 2. So I'm going to say that f prime of pi over 2 from the left is negative 3 sine of 3 pi over 2. Sine of 3 pi over 2 is negative 1, so negative 3, negative 1 is 3. All right, let's find the derivative of 3/2 tan of 2x. So that'll be 3/2, the derivative of tan of 2x is going to be 2 secant squared of 2x. That'll be for x greater than pi over 2. So I'm dropping the equals because I don't know if the derivative exists. And if the limit from the left and the right both exist and are the same, I will then add in the equals. So let's do f prime of pi over 2 from the right, which will be 3 because 3/2 and 2. And then the secant of pi over 2. So the secant of pi, secant of pi over 2 times pi. Sorry, pi over 2 times 2 is the secant of pi, secant squared. Jeez. Okay, 3 secant squared of pi. The secant of pi is, so the cosine of pi is -1, which means the secant is also -1. So we have 3 -1 squared, which is 3, which means we could like throw in an equal sign on either branch here. But the key thing is we can say that f prime of pi over 2 is 3. So the derivative exists and the function is continuous. We can say this function is continuous and differentiable. That's a good one. Okay, let f be the function defined by, defined above, I guess, and c be a positive constant. So that's underlined. That's probably really important. For what value of c, if any, is f continuous? So what we kind of have going on is just like, well, I mean, I don't really know. Quadratic, quadratic. So I'm going to find where they intersect and hope that it's at a positive value. So let's do, like, I don't think we really need to overdo this. We need this to equal this. I'll move it all to one side. I'm going to factor. So -4 plus 1. So either x is 4 or x is -1. So if we let c equal 4, this is going to work for us. Now, do we want to prove it? Not really, but I'm going to do it anyway. All right, so we want the limit as x approaches 4 from the left of f of x, which will be the limit as x approaches 4 from the left of, if you're approaching 4 from the left, you have to use this branch. So 3x squared plus 2x minus 3, which will equal, if you plug in 4, you get 16. 48 plus 8 is 56 minus 3, you get 53. Yikes. The limit as x approaches 4 from the right of, this is if you had to like actually prove it, which you don't have to. Like, we were done. But I'm trying to overdo it so that, you know, we review as many concepts as possible. So this will be the other branch, 2x squared, 5x plus 1. Hopefully this gives the same answer. So we get 16 times 2 is 32, plus 20 is 52, plus 1 is 53, and also f of 4 is 53, because the limit from the right is equal to the value of the function in this case, because of the way it's defined. Therefore, f is continuous at x equals 4. So yeah, if c is equal to 4, this thing totally works. Nice. All right, the function f is continuous and increasing, so I don't know, like that, or like this, or like this. We don't really know the concavity. Based on the values in the table above, what is the best approximation? All right, one more. Consider the function f of x equals x squared minus 8x plus 15 over x cubed minus 9x. We want the limit as x approaches 3. So if I just try to sub in what happens, because sometimes that works, that would give us 9 minus 27 plus 15, which is, is this giving an answer? 27 minus 27, 9 negative 18. This is -3 over 0. This doesn't exist. All right, can we do a better job on that? Probably. I mean, I wasn't expecting that to happen, so, you know, who knows? All right, let me rewrite f of x. Surprising answers. x minus 5, x minus 3. Then I can take out x. You have x squared minus 9, so x minus 3, x plus 3. I'm going to remove the discontinuity. X minus 5 over x, x plus 3. So I definitely got that wrong. This is when x is not 3. So if I plug in 3, I get 9 minus 24. There we go. 9 minus 24 plus 15. This is 0 over 0. But now I know that I can actually do the limit as x approaches, because I've already done the simplification. It's this. There you go. So doing these problems on the fly, this is what happens. You get negative 2 over 3 times 6. Negative 2 over 18. An answer. Okay, that's good. We can also see, because we factored this, that this answer, let me change color. This problem, we're going to get the limit as x approaches 1. I'm going to keep using this factored form now, because why not? X plus 3 is going to be negative 4 over 4, which is negative 1. Nice. And then limit as x approaches negative 3. So this is going to be problematic. We look at it, if we sub in negative 3, we get 0 in the denominator, but not the numerator. So this is going to not exist. If we wanted to, though, we could explore what kind of not existing. So negative 3, 0, and 5. So this is a sign chart for f. And if I plug in negative a billion, I get negative over negative, 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 3 negatives, so negative. Everything is first degree, so there's always going to be a sign change. It's like one of my favorite properties to use for these sorts of things, or you just keep plugging in. But you can see now that we know there's a vertical asymptote right here, right? Because it's a 0 the denominator that does not cancel. So we could say the limit as x approaches negative 3 from the left is negative infinity. So vertical asymptote. The limit as x approaches negative 3 from the right is positive infinity, because we're dealing with a vertical asymptote, so either we get infinity or negative infinity. They're not the same, so the limit as x approaches negative 3 rather, it just does not exist. If they were the same, we could potentially say infinity or negative infinity. In this case, does not exist is the only option. And then the limit as x approaches negative infinity of f of x. I'm going to do the work, but we know the answer is 0, because the degree of the numerator is less than the denominator. So x minus 5. Let's go back to x squared plus 3x. Divide everything by the highest power of x in the denominator. Gives us 1 over x, 5 over x squared, 1, which is the key, and then 3 over x. And then if we go to infinity, we get 0 equals 0, horizontal asymptote. At y equals 0, not the question, but that is true. And there you go. All right, so that's 10 pretty good limit questions for review. I hope this was helpful, and good luck.